Then the third lecture, I thought that it would be good to take bottom-up approach, just to show you how you can be more constructive with the Krauss operator. But the second one, like today, in between, I thought maybe I'll just simply take the mathematician view and can tell you how you can approach the topic from a purely mathematical point of view. A mathematician essentially would just say, look, you have mathematical entities, density operators. You define them mathematically. Roughly speaking, what you said is that a density operator is any operator that is positive semi-definite and has trace 1. I don't care what those entities really are from the physical point of view. They're just mathematical objects, right? So you may say that if you want to, you can be, of course, as sophisticated as you want, depending on what kind of school of mathematics you subscribe. And so you may say, well, this operator is part of a set that are bounded operator on some Hilbert space, whatever. You know, there is a narrative. You can make it mathematically as sophisticated as you want. When you operate with a finite dimensional Hilbert spaces, this notation is a bit overkill because all operators are bounded and so on and so forth, so it doesn't really matter. And anyway, so a mathematician say, well, then let me look at the class of maps that take me from here to another class of bounded operator on some other Hilbert space that preserve the property of density operator. So I want to find the most general class of maps so that if this map takes as an input a proper density operator, it generates another density operator. Another thing that is positive semi-definite that has trace equal to 1. So let's call that class of map positive trace preserving map. And then the question is, of course, you know, you want to characterize those maps somehow. And the thing is, you know, I showed you the maps that we derive from the physical principles earlier today. So the question is, can any positive trace preserving map be represented or has a Krauss representation? So when we have such a map, is it always possible to write it as the sum over I, and then you have operators EI, rho, EI dagger, and you have this normalization condition, of course, that EI dagger EI is equal to the identity. So we're asking this question, is there a sort of implication this way? The most general positive trace preserving maps, does it imply that every single such map can be written in the Krauss form? And of course, you know, it's easy to prove that this is not the case by giving a counterexample, right? So let me give you a counterexample. And there is a classic one. Consider a map that is a transposition. So it takes density operator in a specific basis and generated a transpose of this. So think about a matrix. You have a matrix, you flip it around the diagonal, right? Now, is it positive? Think about eigenvalues, right? So they are just on a diagonal, so it's not going to affect eigenvalues. So if this is positive semi-definite, this is positive semi-definite. So it will preserve positivity, no problem with that. How about trace? Will it preserve the trace? Yes, it preserves, you know, preserves eigenvalues, so it preserves the trace. So clearly, this map is positive and trace preserving map. Now, it turns out that this map is not something that we can implement in the lab. Clearly, this one we can, because we know that any unitary evolution on a huge subsystem, in principle, at least, can be implemented. So therefore, there's always a way to implement a map that is in a Krauss form. So if there's like one liner, like a mantra that you should remember from the earlier lectures, whatever has a Krauss representation is physically doable. It's physically admissible. So Krauss means doable. Now, is this doable? Well, let me show you why it isn't. So it looks like, at the first glance, it takes density operators to density operators, so it kind of works. But consider a scenario where we apply this transpose to a one member of entangled system. So let me just take two systems here. And so let's take the maximally entangled, let's put them into a maximally entangled state. So let's take two qubits. Consider this maximally entangled state that I will call lambda. Let me just write this in dimension d because I may need it later. And it's sum over I. So in particular, and the density operator, the projector on this state is equal to 1 over d, sum over I and j, I, j, tensor, I, j here. So in particular for the dimension 2, you can also write it in the matrix form, so it's going to be 1 over 2. And if you choose the basis 0, 0, 0, 1, 1, 0, 1, 1, it will have entries here. And it's a diagonal matrix, so it's 0 everywhere else. So I don't write 0. So I hope this is clear here. I just wrote the most general entangled state, maximally entangled state in d dimensions for future purposes, but for now, concentrate on maximally entangled state of the type 1 over square root of 2, 0, 0, plus 1, 1. And this system of two qubits in this maximally entangled state is described by this density operator here. Now, what I'm going to do, I'm not going to touch the first qubit, so apply identity to the first qubit, but I'm going to apply transpose to the second qubit. So assume that's doable somehow, and let's see what happens. Now I'm getting into the bottom of the whiteboard that may create a little bit of a problem. So if we want to do this operation, so we want to perform what is called a partial transpose. Identity on the first qubit and transpose on the second qubit. And the state that we want to apply it is 1 over 2. And it has this form sum over ij. In this case, I and j is equal 0 or 1. And it's I, j, tensor, I, j. So the result of this is nothing to this part, so identity to this, transpose this, so flip I and j here. So the result is the matrix which looks like 1 over 2, sum over I and j. The first part is not affected, so we have I, j, tensor, j, I. Another way of doing this, if you prefer to do it differently, so that the partial transpose on the second subsystem essentially means you do the transpose in those matrices in the sub-blocks here in this matrix. So you do transpose here, transpose here, transpose here, and transpose here. That's another way of visualizing this operation. And if you do this, so I hope this part is visible. Well, okay. So if you do this, you can see that, or maybe I'll write it here. It says like 1 over 2, and we get, after partial transpose, we get this matrix. There's 1 here, because the transpose here actually is not affecting this matrix, but this one from here goes here, so I have 1 here, and this one moves here, and this one is here. So you see I have matrix which has this submatrix here. And the question is, if you look at this one, is this a valid density operator? Who thinks it is? Well,
since Technion Artur Ekert wrote a famous paper, I assume that no students at Technion would recognize this.
Right, okay, well, all those people from Technion who think it is not the case that this is density operator. Right, well, indeed it isn't, right? Because if you look at this matrix here, you can see that it has negative, one of the eigenvalues plus minus 1, right? So one of them is negative. So let's sort of stop for a moment and think what happens here. I took what looked like a valid operation that maps density operators to density operators, this transpose. You could see that if you take an isolated density operator, it's perfectly fine. It just preserves the trace, preserves the eigenvalues, so it works. But then what I did, I took an entangled system composed of 2 subsystems, like 2 qubits in the state 0, 0 plus 1, 1, and did nothing to the first qubit identity, and did the transpose, at least mathematically speaking. So now as the result, I got something that is not physical. So if transpose were to be a physical operation, that would be a pure contradiction because we are getting a negative operators after applying the extension of transpose, so like identity on the rest of the universe and partial transpose on something here. So that means that even though transpose is positive trace preserving, the extension, that means like doing identity to everything else and transpose to something that you are interested in, is not positive trace preserving. So mathematically then we have to just make our definition a little bit narrow. We have to actually say that what we require, and this is an extra requirement, is not only that it is positive, but it is completely positive. So this operation has to somehow respect the fact that subsystems in the universe can be entangled. If you have a completely isolated system that is not entangled with anything else, this operation looks perfectly fine. But the real thing is that it's not fine as soon as the system gets entangled with something else. So the class of operators that we really require are completely positive trace preserving. So we go from PTP to something that is called completely positive trace preserving. Now, and if you have completely trace preserving operators, even though I'm not showing this in any sort of proper way at the moment, it is doable, and it can be then written in the Krauss form. So this actually is a very interesting example that sometimes our mathematical intuition, without extra physical intuition, right, can take us can be a bit misleading in this particular case. Okay, so any questions about this?
I have a funny question. What about the fact that if I do this transposition, the commutation relation between spin makers, not with those, you see what that is? It's sigma I, sigma j, the complicated.
Right.
The I sigma k becomes with the wrong sign.
Right. So you change the. It could be. It could be, I don't know. Actually, I don't know the answer to the question. It's a good point, because you change the algebra, right? Which might become unphysical in some sense, but I wouldn't know. Maybe there is a way of expressing this in some other way, or it could be equivalent. So by the way, the transpose is not, yes, please. The completeness is just a phrase which I use by being, the definition of completeness in this case is, complete means that operator is, completely positive, means operator is positive and also positive on all possible extension of this operator. By extension of the operator, I mean doing the operator to, like tracing it with identity on everything else. So that means completely. So in fact, there's more mathematically precise things. So you consider the extension of any dimension. So you assume that you operate on two subsystems, and the subsystem that you don't do anything can be of any dimension. So that's what completeness means in this case. So I want not only this to be positive, but I also want identity terms of this operator be a positive thing. So by completeness, I guess means including everything else to make it complete, if you want to think about it this way.
Wasn't the notion of complete positivity introduced by mathematicians, like Steinspring?
Yeah, so, well, yes. I think that people knew that it's easy to characterize completely positive trace-preserving map because they always admit this form, and that was proven by them. But I think the big challenge mathematically was to characterize positive trace-preserving maps without being completely positive. And I think that was a part of that work. But actually physicists, you can still find, interestingly enough, some textbooks from the early days where people make wrong statements about this. They do not notice complete positivity. So you're probably right that mathematicians were aware about completely positive maps, even though somehow this knowledge was not immediately obvious to physicists who were working in this field in the early days. So maybe you're right. Maybe I shouldn't be just giving this as an example that mathematicians can get it wrong. Maybe it's actually an example that mathematicians had sort of like sniffed that this is actually the right thing, but never related this to sort of like hardcore physics, and hardcore physicists didn't know about that work. So for a long period of time, the two communities didn't talk to each other. So essentially, there was a little bit of a lack of communication. I think that it became all very clear for some reason where people started looking. I think it's sort of late quantum optics, early quantum information science period, I would say. It was maybe a clarifying period for this. Oh, okay, so then, as you mentioned, Choi, that how much more time do I have? Sorry?
We're 20 minutes in.
Oh, okay, fine. So in this case, let me just, as we are talking about purely mathematical stuff, let me just say a few words about something that is, as you mentioned, Choi, and let's go and sort of think a little bit about something that is called state-channel duality. I was asked this question earlier today, so there's a good moment actually to address this question. So we already did something that, namely what we did here was we took a system in maximally entangled state, omega, and applied this map to one subsystem and didn't do anything here. So this was identity here. Now let's take a look. What is actually a most general result of this operation? So let's consider any map that we know now is a channel, is a proper channel. So therefore, the extension of this map is also a channel, is a valid physically doable operation. And therefore, when we start with a valid quantum state, we should get some sort of density operator here at the output, right? So let's look at the form of this density operator. So I have, my input is state omega. If you want to write it as a density operator, as a projector on omega, so the omega, just to remind you, is 1 over square root of d. D is the dimension of the space you are considering here. And you have actually two subsystems of dimension d. And let's write it as, in some basis, you can write it, this maximally entangled state this way. When you take the projector, you would have 1 over d. And then here you would have a sum over I and j. And you have those outer products ij, tensor ij here. So this is the input state here. And now I'm going to apply nothing that is identity to the first part. And I'm going to apply my map E to the second part. So when you do this, of course, then you have something that looks like this. That is equal to 1 over d. It's sum over I and j. And it has I, j here. And then the second term is this map applied to operator I, j. So now, let's think in terms of matrices now. What, this is just a piece of mathematics, but can you visualize it as a matrix? So you know how to form matrices that are tensor products, right? And so you can easily think about the whole thing here as a big matrix, so that, and it's sort of like a block matrix where the entry I, j is a block that has the output of E acting on ij. So it'll look like, if you want, it will look like this. So those are the blocks here, and you put E acting on 1, 1 here. E acting on 1, 2 here. E acting on 1, 3 here. E acting on 2, 1 here. E acting on 2, 2 here, and so on, right? Can you see that? So this is actually how we construct the tensor product matrices. But if you look at this matrix, what is so special about it? So one thing that is interesting is that it contains the full information about the state, the map E. Because if you really want to know how E is acting on any density operator, you know it's a linear operator, right? Or super operator, or linear map. That what you can do, you can just simply express your density matrix in the basis. So you can write it as the matrix element ij, ij. So that's how you decompose the density operator that you want to act on. And then because it's a linear map, it's going to be sum over ij, rho ij, and this operator, super operator of the map acting on ij. Right? So of course then, if you have the result of this, which is another matrix, if you have the result of this for all possible values of I and j, you know how this map acts on basis operator of this type. So you have full characterization of this map. So if I give you this matrix here, you essentially know what the map is doing, because you can simply use the fact that it's linear and decompose it in this way. So we related here the map, a quantum channel, with the matrix, which is the result of this channel acting on one member or one or a half of highly entangled state. So this matrix has a name. I told you that the problem with this field are actually naming things, because there are so many names attributed to so many people that if you don't know those names, you are lost. So this is known as a Choi matrix. And this is part of what is called the state and channel duality. It says essentially, given a channel, I can define a quantum state, which is a Choi matrix, which represents this state. So it goes the other way too. I give you a simple formula how to calculate Choi matrix. So given a map, this gives you the Choi matrix, this expression here. You can also write a compact formula, which is slightly more complicated, how to do it the other way around, but you don't have to, because you see it's just a question of expressing in terms of equations how that we tabulated those values. So you may think about it this way, that a mathematician who wants to know the values of this will just simply tabulate them in the form of a matrix. As it happens, this matrix can be obtained as a result of a real physical process and therefore corresponds to a state. So this goes under the label of Choi matrix characterization of a quantum channel. So it's known as, the phrase quite often used is state-channel duality. It's very simple, in fact. So you can think, if you want to memorize this, think in terms of this diagram here, and know that this diagram will represent a matrix of this type, where it contains, in blocks, it contains total information how the channel acts on matrices that are of this form, that form the basis in the matrix space. Any questions about this? Okay, so so by now we covered completely positive maps, so you should be aware that maps should be not only positive but also completely positive. We covered the state-channel duality. We introduced the Choi matrix. You can see lots of names here. Now, another name one can show, in fact, and this I will leave for you as a form of exercise, that you can go now from the Choi matrix to the Krauss form. And how do you get the Krauss form from the Choi matrix? So it turns out, as a hint, let me tell you that if you have a map and you have a corresponding Choi matrix, let me just call it E tilde here. Now, you can, as any density matrix, you can write it as a mixture of pure state. For example, you can do, I know I shouldn't be doing the bottom of this whiteboard, but let me try this. So you can write it as a sum of IPI, some projector on some pure states, psi I. So you can always represent the density matrix as a statistical mixture of pure states of this type, right? In particular, we have a spectral decomposition where those vectors psi I form an orthonormal basis for the density matrix. They don't have to. It's just we can have a bunch of other decompositions. So it turns out, as a hint, I leave it as a homework for you. It turns out that every single element here, if you decompose Choi matrix into any statistical ensemble, then you can associate a Krauss operator with any vector here, psi I, that is a member of the statistical ensemble. So you can do it, and it's worth a try. If you find it difficult, I'm around, so we can talk. I can tell you how to do it, but give it a try. But assuming that this is indeed the case, you may answer now the question: what is the minimal number of Krauss operators that we need? So suppose I have a map that acts on a density matrix, which is D times D. It can be rectangular, but so suppose we have my density matrix is really a D times D matrix, and then I use Krauss operators to describe a map. And it's a good question, in order to describe the most general map, how many Krauss operators do I need? Is the minimal number that allows me to cover all possible maps? What is actually the minimum? You may be under the impression that the number of Krauss operators has to be enormous because for example, earlier today, we talked about a different representation of subdynamics. And remember, the Krauss operators were associated with the state of the environment. So to each state, we picked up the basis in the environment, and I told you, essentially, we have a Krauss operator acting on the state of the system and the tensor product with the corresponding state of the environment. So you may think, okay, there will be zillions of them because those environments are huge, right? But it turns out if you only deal with d-dimensional system, if it interacts with the environment, it's not going to mess up such a huge Hilbert space. It usually is going to sort of like seriously gets entangled only with the same number of dimensions as it is. So it's not the case that most of those state vectors in the environment are not affected. So you don't have to have a Krauss operators that go through the whole set of the basis states of the environment. But anyway, so never mind this narrative. My question really coming back to this question is, if it is the case that so maybe I'll just back off because let me just go again through this line of the argument. I have a map, a proper quantum channel. This has Krauss decomposition. A certain number of Krauss operators. Now, I also can use channel state duality to associate Choi matrix with this channel. So I construct the Choi matrix. So this channel has the composition of the type, has those Krauss operators Ki dot Ki dagger. So now, I told you that the Choi matrix, being a density matrix, admits a decomposition into a statistical mixture of pure states, okay? So we go from the channel to the density matrix to the statistical decomposition of the density matrix. We know also that the channel has this decomposition in form of the Krauss operators. What I'm telling you now is those one-to-one correspondence between those, that for each element of this decomposition in the Choi matrix, I can associate the Krauss operator. And the question I'm asking you now is, knowing this, can you tell me what would be the minimum number of Krauss operators that I would need in order to be able to describe any map whatsoever? So that, of course, the answer to this question is, what is the minimal number for any density operator if you want to minimize the number of the elements, pure states that form a statistical ensemble associated with this matrix? That would be the spectral decomposition, right? So it has the lowest number of those. And this Choi matrix, what is the dimension of the Choi matrix? D squared. So indeed, you don't have, you put it this way, if you want to represent any map acting on d-dimensional system, you don't need more than d² Krauss operators. Sometimes you may have less, sometimes you can have more, but the thing is, in the worst case scenario, d² is enough. You don't have to actually do more than d². As I say, sometimes it could be less, sometimes it could be more. So in particular for a qubit, what is the minimum number of Krauss operator that we need to represent any map on a qubit whatsoever? 4, right? It's going to be 2². Sometimes we just have channels that have less, sometimes we can have more, but in the worst case scenario, you can always find, you don't have to find more than 4 Krauss operators. So I think that, so that was like a mathematical intermezzo. So I just, in the last lecture, I would like to show you the beauty of the Krauss, okay? In a sense that we'll take a bottom-up approach. I'll just show you that if you just take that everything that is expressed in the Krauss form is doable, then the Krauss form allows us to incorporate also operations such as bring another subsystem that we describe in words usually, or discard that system. So those Krauss operators will be rectangular because they will quite often take you from a system of a given dimension to a system of the higher dimension or lower dimension. Usually when you have this, you reach this stage, when I ask him for questions and there's a silence, there are only 2 options, right? One is that it is completely obfuscated and you didn't get it, or the other one is reasonably clear and obvious, and you don't have any need to ask any questions. But yes, please.
Yes. So can you relate the fact that you need only d² Krauss operators to the unitary freedom?
To what?
The unitary freedom of choosing. So if I have more than d² Krauss operators, how do I think
Yes.
find this unitary that takes me to list?
Yes, you can. So you may think about those Krauss operators as when you look at this unitary freedom, I'm saying that you take like one set of operators into another set of operators. So think about writing those Krauss operators as a big column vector, but they are operators, and then you apply this unitary matrix. So if you have operators that are matrices like D times D, then the basis in this space is d² dimensional. So essentially, you can always pick up an operator basis of dimension d². So therefore, those unitary operators are essentially d² times d² unitary matrices at most. Now, sometimes you can, if you just want, you can also consider isometry, which is, yeah, I simplify things a little bit. In fact, the more proper statement should have been that the Krauss operator can be related by isometry, but never mind. So it's just like you can think that you can relate some number of them by just truncating the. So for example, if you have 2 operators, you still have d² by d² unitary matrix, but you can think about a vector of Krauss operators where there are only 2 entries there and the rest is 0, for example. So this way you go from 2 Krauss operators to say even d² Krauss operators. So this is actually, this is another way of relating this to the unitary freedom. So you essentially thinking about the Krauss operator as a matrix, you don't, the max number of those Krauss operators corresponds to the basis that you need to express this Krauss operator. Thank you.